let's move on to antiderivatives. So here we're gonna, we want to find a function, given a function f of x, we want to find a function capital F so that capital F prime is little f, right? So it's going backwards. So given your function, you want to find another function whose derivative is your original function. By the way, the notation for this, right, this is actually called, we write an indefinite integral. A definite integral is a number, right? An indefinite integral is a function. Actually, it's a family of functions. We're going to write here that the integral of f of x dx with no bounds, right, is actually capital F of x. But then we're going to do this plus c, because if you think about it, there's actually lots of antiderivatives for any function. Like 2x has the antiderivative x squared, but it also has the antiderivative x squared plus 5, because when you differentiate the 5, it goes away, or x squared plus 7, or x squared plus 11, or x squared plus anything. So that's what the plus c is for. So indefinite integral is kind of it's sort of a synonym for antiderivative, but we want the general antiderivative. So maybe I'll write that, the general. What am I doing here? This got so thick all of a sudden. Let's try that again. This is the general antiderivative. The general antiderivative. So let's just do a bunch of these fairly simple examples first. Okay, so let's start with power functions, or power rule. So and in fact, you'll notice a lot of these are the answers to when we did the derivatives of a bunch of problems. So I'm just going to start doing things like writing the integral of 17 dx here. Did I put the dx up there? Yeah, I did. Okay. So we put the dx in because it's because we've seen that the integrals have a lot to do with antiderivatives. So as we know, a function whose derivative is 17 is just 17x plus c, and then we do the plus c, right? If we do the integral of 10x dx, well, that's 10, and then what function has derivative of x? A lot of you probably seen this before. 1/2 x squared works, because when you differentiate the x squared, the 2 comes down and cancels the 1/2. So that's 5x squared plus c. Actually, I should have had a plus c here too, probably. Number 42, if we integrate all of this, anti-differentiate all of this, we get, well, okay, so x to the 10th, think about what happens. A function whose derivative is x to the 10th has an x to the 11th in it. So we know it's going to have an x to the 11th. Just looking at just this part, we know it's going to have an x to the 11th in it. And in fact, when we differentiate x to the 11th, we get exactly 11x to the 10th. So in fact, that's actually perfect. Move it over a little bit. X to the 11th. Similarly, if we, for the x to the 7th term, if we subtract x to the 8th, we differentiate that, we get 8x to the 7th. So that's right. And 4x cubed, well, when we differentiate x to the 4th, we get 4x cubed. So there you go. So that's the answer there. X to the 11th minus x to the 8th plus x to the 4th plus c. If you move on to this one, again, I recommend pausing a lot and trying these yourself. See if you can come up with the answer yourself, especially once you start to see the method a little bit. So here it's going to involve an x to the 3.5 because we're going to add 1. Since we subtract 1 from the power, we're going to end up adding 1 to the power, right? So it's going to involve an x to the 3.5. But then when we differentiate that, this will come down in front, and we'll want to be able to cancel it. So we'll need a 1 over 3.5 in front, right? When we differentiate, that'll cancel the 3.5 that comes down. So plus c. So that works. You could rewrite this as 2/7 x to the 7/2 or 3.5. Okay. Let's look at the next one, 1 over x. Well, we attempted to do the power rule again, like think about adding a power, right? Because this is the integral of x to the -1. But now the issue is if we add 1 to this, we get x to the 0, which is just a constant. And then we divide by 0 because we're supposed to divide by the thing in front. So that's bad, right? And in fact, this is the one outlier when you're anti-differentiating powers, that this one does not, it's not x to the 0 over 0. In fact, we saw 1 over x as a derivative of a function. It's the derivative of the natural log function. And that's kind of perfect. It kind of perfectly steps in as this extra case. Okay, so just try to remember that this is the antiderivative, the integral of 1 over x, the indefinite integral of 1 over x, or the antiderivative of 1 over x is natural log of x. Okay, so when we do the next one, is that natural log of root x? No, it's not, because, well, if you differentiate natural log of root x, that would be a chain rule problem. It would be more complicated, right? It wouldn't just be 1 over root x. It would be 1 over root x times the derivative of root x. So in fact, that's a common thing students do sometimes, is they want to say that is the integral of, or that the integral of this is natural log of root x, but it's not, because this is really x to the -1/2 power. And there we can add, so we know we're going to end up with an x to the 1/2 when we add 1. And then we need something that's gonna, when we differentiate this and the 1/2 comes down in front, we need something to cancel it. So that's in fact 2 will cancel it, right? If you differentiate this 2x to the 1/2, the 1/2 comes down and then cancels the 2. Plus, so that's that plus c, or you could also say 2 root x plus c. Okay, good. Let's just keep going. If we want to integrate the square root of x, that's the integral x to the 1/2 dx. Again, we're going to add 1 to the power, so that's going to be an x to the 3/2. We need something to cancel the 3/2, so that's a 2/3, or 1 over 3/2. Some students would say x to the 3/2 divided by 3/2. But if you divide by 3/2, let's say it was multiplying by 2/3. So, okay. Keep on trucking. Let's just keep going through a bunch of these. Do we need to do all of these? Actually, I mean, you're probably starting to see the pattern now. So, maybe I'll just write these out. So this one I think is going to be 4/5 x to the 5/4. This one is going to be -1 over t. T to the -2, you add 1, you get t to the -1, but you can check that this works, right? Again, not natural log of t squared. This one is -1/5 x to the -5. And differentiate that to check. The -5 comes down in front. This one is -1/10 u to the -10. Okay. -14/3. You add 1, you're adding 3/3. So you're getting -11/3. So I think this is -3/11 w to the -11/3 plus c. This is the integral of x to the 1/3 power. So you're going to get x to the 4/3 power times 3/4. And last but not least, adding 1 to the power is going to give you x to the 1/3. And then you need a 3 to cancel that. Woo. So there's a general thing that maybe I'll just write it over here, that if you have the integral of x to the a dx, that there's two cases. that it's 1 over a plus 1, x to the a plus 1. This is if a is not equal to minus 1. And if a is equal to minus 1, it's natural log of x. Right? Makes sense, hopefully. Okay, so that's the general antiderivative power rule. Okay. Oh, it says it down there. Can you find an antiderivative power rule? All right. And then for these, let me just kind of do some of these real fast. This next grouping. And then the rest will be the more serious techniques, which are like integration by substitution, integration by parts, all these things. Okay, so integral of sine x dx. Well, the derivative of sine is cosine, but that's not what we want. We want the derivative of something to equal sine, but the derivative of cosine is minus sine. So you should check this, but I claim it's minus cosine x plus c because, right, when you differentiate this cosine, it becomes negative sine, and then this negative sine, this negative sine sine, and then this negative sign sine will cancel out that. Okay. So this is actually just sine because the derivative of sine is cosine, so the integral of cosine is sine. This we actually saw as tangent. The derivative of tangent is secant squared, so the integral of secant squared is tangent. Now when we see something like this, okay, so the cosine becomes a sine. So we know there's going to be a sine of 5t in our answer. When we differentiate that, we get a 5 that pops out in front. So kind of like the power rule, we need something to cancel that 5. So in fact, that's going to be a 1/5. Right? You can think about chain rule, or you can think about just what happens when you differentiate this. You get cosine of 5t times the derivative of the inside, which is 5. And so you need this 1/5 to cancel it. Okay, keep on trucking. If I integrate this, I guess I'm sort of saying sine of that times du. Well, it's something very similar. The integral of sine is minus cosine. So there's a minus cosine of 0.01 u. But when we differentiate this, it's going to pop out as 0.01. We need something to cancel that. So we actually need 100 to cancel 0.01. So in fact, there's really going to be a minus 100 here. It's 1 over 0.01, but 0.01 is 1/100th. So 1 over that is just 100. So it's minus 100 times the cosine of 0.01 u. Again, check by differentiating. A lot of times you can sort of figure out the constant, guess at the constant, differentiate to check. If it doesn't work, you might see what you did wrong when you differentiate it, and then you can fix it. All right, just a few more. Oh, this one's nice. Integral e to the x dx is just e to the x. It's its own derivative, so it's its own antiderivative. Integral of e to the 5w dw. It's kind of like the ones we did with sine just now, that it's going to have an e to the 5w, but when we differentiate that, it's going to pop out a 5 in front, so we need a 1/5 to cancel it. So that's that. This one, well, we're going to have an e to the minus x over 3, and we're going to need a negative 3 to cancel the minus 1/3 that pops out when we differentiate it. Last two. Well, the derivative of 2 to the u pops out a natural log of 2 in front. So there's going to be a 2 to the u, and then we're going to have a 1 over ln of 2. You kind of see the pattern here, right? Because now when we differentiate this, it'll pop out the natural log of 2, which will cancel there. And similarly here, this is going to be 1 over natural log of 1.01 times 1.01 to the y plus c. Whew. All right. Well, you get the idea. And then, as I said, we'll go into harder or more complicated integration techniques next. or later. All right. Thank you. Thanks for watching, you guys. I don't know if this is fun or illuminating, but all right. Bye.